Hello, welcome back to organic chemistry. We've been talking a lot about the Michaels reaction. I know you're very excited about the Michaels reaction, like using it. Well, let's put it to use, but now let's do the Stork's enamine synthesis, where we can use an enamine in a type of Michaels reaction. And so let's look at that one. Now, the reason we want to use this type of mechanism is if, say, we have a carbonyl. We have lots of carbonyls, right? And let's say I have this alpha-beta unsaturated carbonyl, and I want to add to it. I want to make an enolate here, and I want to add to that beta position there. Because we did it so many times with the Michaels addition, I want to take this enolate and do the same thing. And I'm going to use what? I'll just say, oh, I'll just go ahead and use LDA. Very strong base. We're going to add that, and then the second step would be A30 plus, right? We're going to make our enolate here, and this is what we want to get. We're going to add at that beta position here, and we're going to have our carbonyl back there, right? Can we do that? We can't do that. We wouldn't be able to see this reaction. 1, 2, 3, 4. This reaction wouldn't happen. We'd see no reaction. We get no reaction. Or at least we wouldn't make that product. Because we talked about this already, right? We talked about this enolate being what? It's being a very strong enolate. If I took this, reacted with my LDA, and made my enolate with that, this enolate is going to attack what? It's a very strong enolate. This one would come by, and it wouldn't worry about attacking the beta position. This one would then go ahead and attack that position there. This would be a very strong nucleophile. That'd be a 1,2 addition nucleophile. So we'd end up attacking that carbon of the carbonyl. And we get something like that, right? And we can go on and on with that one. But we couldn't be able to get this beta addition here. We couldn't do that. We couldn't add that beta carbon because, again, this nucleophile is too strong. This is a 1,2 addition nucleophile. I know you're saying, I really want to make an enolate at this position here. I really want to add it at that beta position there, okay? I want to do that. But we can't do it with our normal forming our enolate and attacking that. So we have to do something a little different. This is where we get this enamine comes from. And we've played with enolates a little bit before, right? We made enamines before, but we didn't really do anything with them. But now we can start using them in some chemistry. So let's make our enamine, and let's talk about that. So if I take my carbonyl and I react it with, let's see, to make an enamine, we're going to need a secondary amine. And we're going to need some acid. Let's just use TSOH. Use a strong acid here. And we've gone through the mechanism already about this. We know what's going to happen. Oops. We get that molecule there, right? We spent some time going through the mechanism of this. It's in a previous video where we go through the mechanism to make this as our final compound. But now we made this, what can we do with it? There's always something we can do with it, right? Well, we can use it as a nucleophile. And what's interesting about this, let's draw a resonance structure of it. And they can help us determine, is there anywhere placed on this molecule to be nucleophilic? So remember, there's a lone pair of electrons on nitrogen. Electrons come down. These ones come out here. Look at that. And so by doing this, we end up with that negative charge here at this carbon, and this nitrogen here is going to have a positive charge on it. So in our molecule here, we have a partial negative charge on this carbon here. This would be a great nucleophile. Not only that, this is going to be, and actually it's going to be a 1,4 addition nucleophile. Which is kind of helps us out a lot, right? It's going to be a 1,4 addition nucleophile because, again, it's not a very strong nucleophile, not compared to, say, just a traditional enolate. Not as strong of a nucleophile as, say, to a Grignard, right? So it's not going to be as strong. So it's going to be our 1,4 addition nucleophile, which is perfect for us because we can use that to add to that alpha beta unsaturated carbonyl at the beta position. So now I can take this group here. And so what we can do then is, once I have, let's just play around with it a little bit. This one can then go to what? It can then add to our position at our beta carbon here, like that, like this, just like we've seen before. We've seen this, right? We saw this previously. Now we've done this. Oops, positive charge there. Like that. Okay. And so we've added this group on here. And we've done the rest of this story, right? Where we can take this, it can, electrons come back down, we can pronate this, and then we can take care of this, right? So this is a nice way of getting around this idea that I can make my carbonyl into an enamine, and then use my enamine to do some chemistry, do that 1,4 addition. Now let's look at this, now that we've kind of talked about it, let's actually go through a situation and actually use it in real life. Let's put some reagents in. Let's try it again. Now I'll show you the best part about this is right at the end. So let's take our, let's use this one here. And what we're going to do is we're going to first use our secondary amine with a little bit of acid. Second step is going to be then what? It's going to be addition of our enolate, or actually, I'm sorry, alpha beta unsaturated carbonyl. Let's go ahead and use this one this time. Let's use this one. That'll be fun. And the last step is going to be H3O plus. And what's kind of cool about the H3O plus at the end is that we'll show what we can do with it. We actually can take care of getting back our carbonyl at the end. Let's talk about that. All right, so we're not going to show too much of the mechanism of this because we've gone through these mechanisms already in previous videos. You go back and watch those videos and talk about how do you make an enamine. You go through the mechanism, how to do that. How to attack the alpha beta, we talked about that. We'll do that a little bit. And so let's go through the different steps of this mechanism. So I'll do kind of a pseudo mechanism because we've done a lot of these already. So let's take our carbonyl first. We're going to first react it with our, oops, let's draw this a little bit lower. So we're kind of out of the way. All right, so the first one's going to be what? Nitrogen group here. This is going to be with our acid. Just a little bit of acid in there. And we're going to end up generating this species here. We generate our enamine. Then our enamine gets treated with our alpha beta unsaturated carbonyl. And just like we saw before, these electrons are going to come down. These are going to attack here. Electrons pop up here. This comes here. This goes here. And this is where that carbon group is going to be added to. So we're going to add that group there. This goes here. With that positive charge there, right? So all we've done here is we've done the first two steps. We've done step 1. We did step 2. Step 1, we made the enamine. Step 2 is then introduce the alpha beta unsaturated carbonyl, which then our enamine attacked. And then we're at this point here where our oxygen then has a negative charge on it. Now, our final step is going to be H3O plus. And when we added H3O plus, and we'll do this over here, a couple of things are going to happen. We're going to add in the H3O plus. It's going to protonate the oxygen here, right? And we're going to have that tautomerization where we go from this enol to the carbonyl. So we're going to generate our carbonyl back here. More importantly, over here, this enamine. In our previous videos, we talked about with enamines, when we expose them, treat them with H3O plus, what happens? They're going to hydrolyze and give us back our carbonyl, which will be great for us. We're going to get our carbonyl back from this. And so at the end of this, Again, we're not going to really go through the mechanism of this because we've seen that mechanism already. Is that we're going to get to this spot here. We're going to get to that form there, where we get our carbonyl back. We started with the carbonyl. We got our carbonyl back here. And we have another carbonyl here. So really, from doing this type of reaction, by adding this step here with this enamine step here, we're actually able to take an enolate and do a 1,4 addition. Previously, if I just made this an enolate and try to attack this, it would go after that carbonyl. Carbon of the carbonyl. Would go after that carbon of the carbonyl. Wouldn't even touch the beta one. Wouldn't even look at it. But once we make this into the enamine version here, then we make this into that nucleophile that's not as reactive. So it's going to be a little bit slower. So it's going to go after that beta position. It's going to go after that beta position of the alpha beta unsaturated carbonyl. And so we're able to attack here. We're able to attack here, make this new bond here, and then we're able to hydrolyze it to get our carbonyl back. So it's essentially like we made our enolate attack the beta position, but we had to go through this step to do that. So it's a great way to add your carbonyl based on your strategy and what you're trying to get to, planning things out. So if I want to enolate here, and I want to go through making some larger molecule that has a weaker enolate, I can do this Stork enamine synthesis to do that and put these groups on here, right? We're getting to the point where there's so many different ways we can do things. We can almost build anything now, right? So we'll keep doing that. We'll keep building stuff.